everyone, myself Babitha, working as a assistant professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal. Today I am going to discuss about half-wave rectifier and its analysis. So before going to the half-wave rectifier, first of all we have to know what is meant by rectifier. So rectifier is a electrical circuit which is used to convert the AC energy into DC energy, that is nothing but alternating current form into direct current form. So these are some type of rectifiers we can observe here, different types of rectifiers. So here we are going to discuss about what is meant by rectifier and what is meant by half-wave rectifier and the analysis part of half-wave rectifier. So I have already mentioned rectifier is used to convert the AC form into DC form. Actually, why require this particular rectifiers? These rectifiers are used in the power supply units in order to convert the AC voltage into our required DC form for the required applications. So in the power supply units, we are having the transformer first. So for this transformer, we are going to provide the 230 volts AC supply. So here transformers are of two types, step-up transformer as well as step-down transformer. So transformer is used to convert one form of energy into another form. So here we are going to use the step-down transformer. So it will convert the 230 volts into required 9 to 15 volts for the desired application. So here we are getting the step-down voltage in the form of AC. For the input of the transformer, we are providing the 230 volts AC. So the output of the transformer, we are giving to the rectifier. So rectifier will convert the AC voltage into DC form. So even though after performing the rectification process, we are having along with the DC content, some amount of AC content is also present. So in order to remove that AC content, we are going to use the filter. So filter is a circuit which is used to remove the AC contents which are present in the rectifier output. So this is the filtered output, and after filtering we are giving to the regulator. So the function of the regulator is to stabilize the required DC voltage without any fluctuations, and from that regulator we will get the stable or constant DC voltage without any fluctuations that we can use for our applications. So this is a power supply unit. So in this power supply unit, here we are going to use the rectifier for converting AC into DC form. So these particular rectifiers are of three types. One is half-wave rectifier and full-wave rectifier and bridge rectifier. So how we can differentiate particular rectifier belongs to which type of rectifier? That is depends upon conduction period of the rectifier. In the case of half-wave rectifier, it is going to utilize the positive half cycle of the applied input voltage for converting AC into DC form. So that's why it is called as half-wave rectifier. So in the case of full-wave rectifiers, we are having two types, center-tapped full-wave rectifier as well as bridge rectifier. In the case of full-wave rectifier, we are using the center-tapped transformer and we are going to utilize total full cycle of the applied input voltage for converting AC into DC form. And similarly, in the case of bridge rectifier also, we are going to utilize the total full cycle of applied input voltage for converting AC form into DC form. But what is the basic difference between the center tapped full wave rectifier and bridge rectifier means? In the case of center tapped full wave rectifier, we are going to utilize center tapped transformer instead of normal transformer, and we are going to utilize 2 diodes. And while in the case of bridge rectifier, instead of again center tapped transformer, we are going to utilize the normal step down transformer, and instead of 2 diodes, we are going to utilize 4 diodes in the form of bridge. So because of this constructional differences, we can call it as it is the center tapped full wave rectifier, and one more one is the bridge rectifier. So in this session, we are going to discuss about the half wave rectifier. So this is the half wave rectifier. To construct the half wave rectifier, we require one step down transformer. This is your step down transformer. Okay. And one PN junction diode. This is the PN junction diode, and one load resistor in order to control the flow of current in the circuit. And for the transformer, we are providing the 230 volts supply. 230 volts supply. So this is the pictorial representation of the half wave rectifier. So same thing I'm going to represent in the form of circuit. So this is the half wave rectifier. Okay, 230 volts supply. And it is the step down transformer so that it will convert the high voltage into low level voltage form. So here I'm using the AC signal as the input voltage, and I'm going to apply the positive half cycle ones as well as the negative half cycle ones in order to see the operation of the half wave rectifier. First of all, I'm taking the positive half cycle from 0 to pi here. I'm applying to the rectifier here. So here we will get the positive half cycle first, 0 to pi. Here it is 230 volts only. Here it is step down transformer. We'll be getting here it as 0 to pi, and pi to 2 pi it is negative half cycle. So this positive half cycle across the secondary of the transformer is applied to the diode here. So once we are taking the positive half cycle means across A we will get the positive and across B we will get the negative voltage. So once we are providing the positive voltage to the anode terminal of the diode, this is the anode terminal of the diode and this one is the cathode terminal of the diode. So once we provide the positive voltage to the anode terminal of the diode, so because of the forward bias, the diode will enter into the conduction state and it acts like a closed switch. And it acts like a closed switch, and the corresponding current will flow in the load resistance RL. You get the load resistance RL. So what is the output voltage we are getting here? It is for the positive half cycle is, that is V0. How much we are getting here? It is how much input voltage, how much positive voltage we are getting, that much we are getting for the positive half cycle of the input signal. Why? Because there is no other components are there for conduction as well as voltage drop. So that's why how much input voltage we are providing, so that much we are getting across the output of the rectifier or else across the load resistance. And similarly, the output current IL also we are getting same, how much we are providing the input voltage, 0 to pi range. So this is the case when we take the positive half cycle for the rectifier. And similarly, if we take the negative half cycle from pi to 2 pi, so when we apply this negative voltage from the secondary of the transformer to the diode, at that time the potential across A is minus and across B it is positive. So that is nothing but for the anode terminal of the diode we are providing the negative voltage. So that is nothing but your diode is going to acts like a open circuit here. Diode is open circuited here. Okay, diode is open circuited. So once the diode is open circuit means it provides very high resistance path so that there is no flow of current through the load resistance RL and there is no output voltage. So during the negative half cycle we are not getting any output voltage as well as we are not getting any output current. So because of this reason we are calling it as half wave rectifier. It is going to utilize only the positive half cycle of the input for converting into DC form. So that's why it is called as half wave rectifier. And next we will see the analysis of half wave rectifier. So in that we are going to calculate DC output voltage as well as DC output current, and we are going to calculate RMS values of voltage and current and how much efficiency we are going to get in the half wave rectifier and how much regulation factor we are going to get and how much transformer utilization factor we are going to get and peak inverse voltage, form factor as well as peak factor. So in the analysis part we are going to calculate all these parameters. So before going for the analysis, first of all we have to know how much input voltage we are getting and how much output voltage as well as output current we are getting from the output of the rectifier. For that I am considering my input voltage as, okay, my input voltage as VI equal to Vm sin omega t. So this is for 0 to 2 pi range. So this one we are taking here it as where Vi equal to plus Vm sin omega t for the duration 0 to pi and Vi equal to minus Vm sin omega t for the duration pi to 2 pi. So for the positive half cycle plus Vm and for the negative half cycle minus Vm we are providing for the rectifier. And we are assuming the diode as ideal one. Ideal diode. So once the diode is in ideal form, so the forward resistance of the diode in the forward direction is, I am taking here it as RF as well as the reverse resistance of the diode once it is in the off state or in the reverse bias condition as reverse resistance, that is RR. So here we are assuming it as the ideal diode. So the forward resistance is RF and the reverse resistance is RR. So once we are applying this particular input voltage to the half wave rectifier, we will get the corresponding output current across the load resistor RL, that is nothing but IL. IL equal to Im sin omega t. So this particular output we can expect within the duration from 0 to pi range, and from pi to 2 pi this value is 0. Why? Because only for the positive half cycle we are going to get the output. For the negative half cycle we are not getting any output, so that's why it is 0. Where what is mean by Im here? Im is nothing but the maximum amplitude of the obtained output voltage. So how we can calculate this Im equal to Vm by Rf plus Rl. So here Rf is nothing but the forward resistance of the diode and RL is nothing but the load resistance. In the rectifier we are having only two components, diode as well as the load resistor. So that's why we are considering the two resistance, voltage resistance across the diode as well as the load resistance. So to find the maximum value of the or maximum peak of the output current, we have to use Vm by Rf plus Ra. Where what is mean by Vm here? So this is the maximum value of supply voltage. Okay, maximum value of supply voltage. So these are the things required to calculate the parameters of the half wave rectifier. So in this we are going to calculate first DC output current. We can represent here it as I subscript DC. This is nothing but average current, how much we are getting from the output of the half wave rectifier. So this one we can calculate from the waveform of the output waveform of the current here, 0 to pi to 2 pi. So only positive half cycle we are having, but to calculate the average value we have to take the total full cycle. So that's why here it is IDC equal to 1 by 2 pi integral of 0 to 2 pi I d omega t. So where I equal to how much here? I equal to Im sine omega t. So now substitute the value of I in the above equation. So what we will get? 1 by 2 pi integral of 0 to 2 pi Im sine omega t d omega t. So if we observe the output waveform, from 0 to pi we are having one value, and from pi to 2 pi we are having 0. We don't have any output current. So we can write it as, I am taking 1 by 2 pi integral of 0 to pi, it is Im sine omega t, okay, plus from pi to 2 pi this value is 0. This value is 0. So what we will get here, I am taking Im outside, Im by 2 pi integral of 0 to pi sine omega t into d omega t. So if you apply the integral, here it is Im by pi integration of sine omega t is nothing but minus cos omega t. Limits are from 0 to pi. Okay, limits are 0 to pi. So Im by pi into minus of cos pi is minus 1, minus of cos 0 is 1. So here it is 2 Im by pi. So here it is 2 pi. So this 2 will get cancelled. So here it is Im by pi. So IDC value we are getting here it as Im by pi. So if we substitute the value of Im over here, we will be getting here it as Vm by pi into Rf plus Rl. So we can utilize this particular formula as well as this particular formula to calculate the IDC, Im by pi or Vm by pi into Rf plus Rl. So this is the DC output current we are getting from the output of the rectifier. And next one is DC output voltage. That is nothing but VDC. To calculate DC output voltage, we are representing here it as VDC, that is equal to IDC into R. And next IDC value is Im by pi into R. Substitute the value of Im, that is Vm by pi into Rf plus Ra. So here the load resistance value RL is far greater than the forward resistance of the diode RF. So if we take the RL common here, Vm into RL by pi into RL, that is 1 plus RF by RL. So here if the load resistance value is very high, means this total value will be reduces. So we can neglect that value is less than 1, so that we can neglect that. We will be getting here it as Vm by pi. So VDC value here it is Vm by pi. IDC value we got it as Im by pi, as well as VDC value we got here it as Vm by pi. So next we need to calculate the RMS value of the current. That we are representing here it as IRMS. So to find the root mean square value, we have to take here it as 1 by 2 pi integral of 0 to 2 pi I square d omega t under root. Now substitute the value of I here, that is I equal to Im sine omega t. 1 by 2 pi integral of 0 to pi it is I square d omega t plus from pi to 2 pi, this value is 0. Why? Because we are not getting any output for the negative half second. Total under root. Now substitute the value of I, that is 1 by 2 pi integral of 0 to pi Im square sine square omega t d omega t. So this pi to 2 pi value is 0. So total under root. Next I am taking Im square outside, that is Im square by 2 pi, and I am writing sine square omega t as 1 minus cos 2 omega t by 2 d omega t. Total under root. So I am taking these two also outside, that is Im square by 4 integral of 1 minus cos 2 omega t into d omega t. Whole under root, that is Im square by 4 integral of 1 is omega t with the limits 0 to pi minus cos 2 omega t integral is sine 2 omega t by 2 with the limits 0 to pi. So this overall under root. So Im square by 4 is pi minus 0 for omega t minus of sine pi is 0 minus sine 0 is also 0. And in under root. So we will be getting here it as Im square by 4 pi into pi. So overall under root. So if you apply the under root to this, we will be getting here it as Im by 2. So IRMS value we are getting here it as Im by 2 in the case of half wave rectifier. So in this way we have to calculate the RMS value of the current. And similarly, to find the RMS voltage, that we are indicating here it as V subscript RMS. To find the VRMS, we have to take IRMS into RL. We have already calculated the IRMS value, and that is equal to Im by 2. Substitute that IRMS value here, that is Im by 2 into RL. And next, we know the value of Im, that is equal to Vm by Rf plus RL. That is Vm by 2 into Rf plus RL into RL. And here, load resistance value is very greater than the forward resistance of the diode. So in this case, if we take the RL common in the denominator, we will be getting here it as 1 plus Rf by RL into RL. So this value is very less, so we can neglect this. We will be getting here it as Vm by 2. So Vrms is equal to Vm by 2 in the case of half-wave rectifier. And next parameter is the efficiency. So in order to see the performance of any circuit or any device, we have to check the efficiency of that particular device. In order to check the efficiency, here we are having the formula DC power delivered to the load divided by AC input power from transformer secondary. So we are representing here it as PDC by PAC. So how to calculate this DC power as well as AC power here? So PDC we can calculate here it as IDC square into RL. So this one we can find directly. But while coming to the AC power of the half-wave rectifier, here we are having two AC powers, that is PA plus PR. So where what is mean by this PA and what is mean by this PR? PA is nothing but the power dissipation across the diode. Okay, PA is the power dissipation across the diode, that is IRMS square into RF. And similarly, PR is nothing but the power dissipation across the load resistance RL. That is nothing but IRMS square into RL. So the total AC power is equal to sum of the power dissipation across the diode plus power dissipation across the load resistance RL. So that is equal to IRMS square into RF plus RL. So now substitute this DC power as well as AC power in the case of efficiency. That is PDC by PAC is equal to IDC square into RL divided by IRMS square into RF plus RL. So now substitute the values of IDC as well as IRMS here. So the value of IDC is Im by pi and the value of IRMS is Im by 2 in the case of half-wave rectifier. So if we are substituting that value, Im by pi whole square into RL divided by Im by 2 whole square into RF plus RL. So here Im will get cancelled. So we will be getting here it as 2 by pi whole square into RL by RF plus RL. So we can calculate here it as so in the denominator the value of RL is far greater than RF. So we can write it as 2 by pi square into RL by RL into 1 plus RF by RL. So we can neglect this value. Why? Because load resistance value is greater than the forward resistance of the diode. So the total value is less than 1. So we are neglecting that. So this one we are getting like this. So this one 0.406 divided by 1 plus RF by RL. So if we write in terms of percentage, we will be getting here it as 40.6% when we neglect the RF by RL ratio. In the theoretically, if we neglect the RF by RL ratio, we will be getting here it as 40.6% efficiency in the case of half-wave rectifier. And next factor is the ripple factor. So this ripple factor indicates how much amount of AC content which we are getting across the output of the rectifier. Actually, after rectification, we need to get the DC content only, but along with the DC content, some amount of AC content also we are getting across the output of the rectifier. So we have to calculate how much that AC content we are getting along with the DC content. That we can calculate by using the ripple factor here. So this one is defined as the ratio of effective value of AC component to the direct value of the voltage or current. That is nothing but we have to take it as RMS value of AC component to the DC value of the signal. That we are indicating here it as ripple factor we are representing with gamma. So to find gamma, we are taking here it as V gamma of RMS divided by VDC. That is nothing but AC content which is present in the RMS voltage divided by average voltage. So to find the V gamma of RMS, we have to take VDC square minus VRMS square under root. Okay. So to find the ripple factor, we are taking under root of VDC square minus VRMS square by VDC. So if we simplify this, we will be getting here it as 1 minus VRMS square under root. So after simplification, we will be getting here it as VDC square, that is 1 minus VRMS square by VDC square under root, that is equal to, we will be getting here it as under root of VRMS by VDC minus 1. So if we substitute the VRMS value as well as VDC value here, we will be getting here it as 1.21. And if you write in terms of percentage, this value is 121%. So the ripple factor in the half wave rectifier is 121%. So that is very high value. In the rectification, we require the DC content, not the AC content. But because of the half wave rectifier, we are going to utilize only half of the power for conversion of AC to DC. So that's why we are getting much amount of AC content compared to the DC content in the case of half wave rectifier. And next one is regulation. So regulation is nothing but, even though if you vary the load voltage, the output voltage should be constant. That is nothing but if you vary the load resistance value, that corresponding variation we can observe in the output current. So if the same variation we can able to see in the load voltage, that is nothing but output voltage, but that is not required here. So regulation means it should provide the stabilized or constant voltage without any variations. That is nothing but if we vary the load resistance also, we need to get the stabilized voltage. So to find the regulation here, we have to take the variation in the output DC voltage with change in output load current. Okay, that we are taking here as the regulation. To find the percentage regulation, here we are having the formula, that is V no load minus V full load by V full load into 100%. That is nothing but we have to calculate the output of the rectifier without load resistance, that indicates the V no load, and we have to calculate the output of the rectifier with load resistance RL. Then we have to substitute the two values to find the regulation. So this regulation factor should be minimum in order to get the stabilized voltage, stabilized DC voltage for the load. And next one is transformer utilization factor. So this transformer utilization factor indicates how much amount of AC power is utilizing in the half wave rectifier for conversion of AC to DC. That indicates the transformer utilization factor here. So to find the transformer utilization factor, we have the formula here. It is DC power delivered to the load divided by AC rating of the transformer secondary. That is equal to PDC by PAC rated. So here PDC value is We know already it is IDC square into RL. But PAC rated is nothing but this is the rating of the transformer secondary. To find this PAC rated value, we have to know the how much RMS voltage which is flowing through the secondary of the transformer, that is Vm by root 2, and similarly how much RMS current which is flowing through the secondary of the transformer, that is Im by root. So the total rated AC power is the multiplication of this RMS voltage through the secondary into RMS current in the secondary of the transformer. So after simplification and after substituting the IDC value here, we will be getting here it as Im by 2 whole square into RL divided by Vm into Im by 2 root 2. So we will get this value as 0.287. That is nothing but 0.2% of the AC power is going to utilize for conversion of AC to DC. In the case of half wave rectifier, it is very, very less value. And next one is peak inverse voltage. Peak inverse voltage is nothing but when the diode is in the reverse bias condition, how much voltage we are getting across the diode in the half wave rectifier. And also we can say how much reverse voltage the diode can withstand in the reverse bias condition is also indicated with the peak inverse voltage. So in the case of half wave rectifier, we are taking the positive half cycle. In that case, we are getting the output. But in the case of negative half cycle, we are providing the voltage as minus Vm. So in that case, it is not providing any output voltage as well as any output current. During the negative half cycle, half wave rectifier is not going to provide any output, but how much input voltage we are applying? We are applying minus VR voltage. So the amplitude of that minus VR is Vm. So the maximum voltage we are applying in the reverse bias condition is Vm. So the peak inverse voltage of the half wave rectifier is Vm. So that is nothing but when the diode is in the reverse bias condition, how much input voltage we are giving here, it is Vm. So that indicates the peak inverse voltage. And also how much reverse voltage the diode can withstand is indicated with the peak inverse voltage. That is nothing but without damage or without breakdown, till what extent, till what voltage the diode is going to work properly in the half wave rectifier is indicating with the peak inverse voltage. And next one is form factor. So to find the form factor, we have to take the RMS value of the voltage or current to the average value of voltage and current. And generally form factor we will represent with F. So I am taking in terms of current. So IRMS divided by IDC. So substitute the values of IRMS and IDC here. IRMS value is Im by 2 and average or DC current value is Im by 5. So if you substitute the two values here, Im by 2 divided by Im by 5. So we will be getting here it as pi by 2, almost we will get it as 1.57. So the form factor in the case of half wave rectifier, we are getting here it as 1.57. So while coming to the advantages of half wave rectifier, so it is very simple circuit and it is available with less cost and we can design very easily this particular half wave rectifier. Why I am telling like this means to construct the half wave rectifier we require only three components here, that is the transformer, diode and the load resistor. So if we connect all that components we can get the half wave rectifier. Okay, and the cost is also very less. Why? Because the resistor diode cost is very less, but only the transform cost is high. But if you see the overall cost of the half wave rectifier, it is very less. And size of this one is also less. Okay. While coming to the disadvantages, it is going to utilize only half of the power for conversion of AC to DC. That is the basic drawback. Why? Because of utilizing the only half power, it is providing the efficiency as very less, that is only 40.6%. So once we are designing one particular circuit, mean we are expecting some 99% to 99.9% efficiency, but in the case of half wave rectifier we are going to get only the 40.6% of the efficiency. So that is the major drawback. And the transformer utilization factor is also very less, that is almost some 0.287. That is also because of the reason of less utilization of the AC power available across the input for the rectification. Okay, transformer utilization factor is also less. So these are the disadvantages of the off-wave rectifier. So in the analysis part, and one more disadvantage here, it is the ripple factor is 1.21. That is nothing but 121% of the AC content we are getting along with the DC component. That is the major drawback. These three are the major drawbacks of the half wave rectifier. So in order to overcome these disadvantages, next we are moving for the center tapped full wave rectifier or bridge rectifier here. In that we can improve these particular parameters. We can improve the efficiency as well as transformer utilization factor as well as ripple factor. So these parameters we can improve in the case of full wave rectifier, and instead of like that we are going to utilize total full power for conversion of AC to DC in the case of full wave rectifiers. So these are the advantages of full wave rectifier compared to the half wave rectifier. So to overcome the disadvantages of half wave rectifier, we are going to utilize the full wave rectifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.